Here this is PV plus DFIG, that is providing the supply to the grid and the load. DFIG here, the number of turbines is 6 and the nominal power is 1 megawatt. Line to line voltage is around 575 volt. This data we have to enter frequency 50 Hz, and rotor side nominal voltage it is around 2 kilovolt. Okay, these are induction motor parameters. Stator side, rotor side, magnetizing inductance, those things, and converter datas. It is the maximum current at grid side inverter. Coupling inductor value, nominal DC voltage 1150 volt. Capacitor values. Turbine data, that is wind turbine data. Mechanical power is 1.5 megawatt. And here wind speed 11 meter per second. Initial wind speed same 11 meter per second. Okay, and this is drive train, that is how much times the torque should increase from wind turbine to generator. The shaft is connected. Okay, here for one single rotation of the wind turbine, how much rotation should be provided to the generator, that is provided here. The torque can be adjusted here. And control parameters, that is PI controller parameters, DC voltage regulation, KP and KI value, current grid side converter, current regulation, inner current control regulations, and for rotor side control, speed regulation, rotor side converter current regulation, and reactive power and voltage regulation. Okay, for all the PI controllers, we are providing the KP and KI values. And for pulse generation, what is the frequency that is provided? Okay, and that will be connected. And this is the voltage and current measurement from the DFIG. From that, power can be calculated. And it is stepped up here while connecting it to the grid from 570 to 35 kilovolt. And it is connected to grid here. Again, it is stepped up 35 kilovolt to 220 kilovolt. And here we are creating the fault at the time interval of 0.2 to 0.25 seconds. Three phase to ground fault. Okay, and we are providing the power to both load and the grid. That is when PV is available, PV will be providing. When grid is, sorry, DFIG is available, DFIG will provide the power. And these are the voltage of that DFIG, voltage and current. At 0.2 seconds, the fault is created. So it is affecting the DFIG also here. And this is DC voltage. Here if you see means it is 1150 volt, that is the nominal DC voltage. And after 0.2 seconds, when fault is created, the DC voltage here it is increased to 1600 volt. Okay, it will affect the converter devices. Again, when the fault is cleared, the DC voltage is reduced and settled at the nominal value. So when the fault is occurring, the voltage is increasing at the DC link, and current is also increasing. And these are the voltage and current at the grid side. Here at grid side, the current is increasing nearly 40 per unit to 60 per unit, where the nominal value is 1 per unit. So 60 times it is increasing. and these are the at the load side. Due to the reduction in the power due to that three phase to ground fault, here the both voltage and current is decreasing in this load side. When the fault is created at grid side, it is affecting the load performance also. So these are the thing, voltage and current values and the DC link voltages when the fault is occurred. It is affecting the DC link of the DFIG. So if the DC link is affected, that is the voltage is increased, it will affect the components of rotor side converter and grid side converters. We should avoid the scenario by introducing the Crowbar protection. Okay, in this we have introduced the Crowbar protection. That is, we are providing the least resistance path when the fault is occurring. Here the fault occurring time can be uh, sensed by this fuzzy controller. Here the fuzzy controller is checking the DC link voltage and the current, grid current. The magnitude of the grid current is measured here. This is grid current. From that the magnitude is measured here, and it is compared with the reference, that is nominal current 1 per unit, and the error is provided here to the fuzzy controller. Here it is three phase, so the average value we are taking it here and provided to the fuzzy controller. Similarly, here DC link nominal voltage is 1150, that is compared with the DC link voltage here, and error is provided here. It is converted into per unit, that is 1 by nominal voltage. We will get here per unit error, and that per unit error is given to fuzzy controller here. So here this is the name of the fuzzy file, that is control.fis, that can be opened with this fuzzy command. Fuzzy, type fuzzy in command window before running the simulation. Here one dialog box will open. In this file, import from file. I have sent the fuzzy file control.fis that have to be imported here. This one. Okay, now the fuzzy is opened. That is fuzzy file is opened. We have to export it to workspace. Here the name should be control dot, yeah, control. Workspace variable name should be control. Then it will be exported to workspace. Here, this is control. Okay, fuzzy file. After that, we have to run the simulation. Here we have to run the simulation. And here in this, if you see, I have provided the resistance value as 0.01 to offer the minimum resistance path, and it will be provided to the ground. That is, when the fault current is provided, when fault current is flowing here, these switches will be on by the help of this fuzzy controller. And when the switches is on, at the time, here the fault current will flow through this least resistance path to the ground. So it will not affect the DFIG components or these transformers. Here if you see means this is the grid current. Okay, without that crowbar protection, it is nearly say 40 to 60 per unit. When the fault is occurred, now it is 1.5 per unit. And here this is the DC link voltage. Initially when the without protection, it is increased to 1600 volt. After the fault is cleared, it is reducing to nominal value. Here it is due to the crowbar protection, the voltage is decreased here because due to the introduction of the crowbar, all the current fault current flows through the crowbar resistance. So here the voltage is reduced here. That is, we are providing alternate path to the fault currents. And when the fault is cleared, again it is reaching the nominal values. So due to that, the components in the rotor side converter and grid side converter will not be affected. Here if you see, this is the output of the fuzzy. Initially it was 0.3. At 0.2 when the fault is occurred, here it is increased up to 0.8. And when the fault is cleared, it is again reaching the 0.3. So we have provided the command here. When it is greater than 0.5, the pulses should be on. That is, these switches will be turned on. When the switches are turned on, the current will flow through the resistance from the system to the resistance to the ground. Is simple in operation. This will not compensate the fault. It will just create the alternate path in order to safeguard the components. This is the DFIG voltage and current. And here, these are the load voltage and current and load power. It is simple in operation. And here these are the rules. That is, if input 1 is maximum, that is this is maximum, and input 2 is minimum, the output is minimum. If input 1 is medium, and if input 2 is minimum, output should be maximum. Same here, both are minimum, output should be maximum. According to these rules, the output will be generated, and according to the output, the crowbar switches will operate. This will offer the protection to the components until the circuit breakers will start to operate. It is the particular region is shut down. Still, we have to tune it in order to reduce this here. This current should be further reduced. Until then, we have to tune the resistance values. These resistance values, depending upon that only, the current is flowing through these resistances. We have to calculate this resistance and tune it accordingly. Similarly, fuzzy also, we have to tune the rules in order to increase the execution speed. The principle is the crowbar production offers the minimum resistance path when the fault is occurred, so that all the fault current will flow through the crowbar resistances and it is passed to the ground, so that all the other components will be protected. This is the basic principle.